Okay, guys, welcome. Today we're going to talk about Eulerian walks and Hamiltonian cycles. Now, to introduce this idea, we're going to talk about the famous bridges of Konigsberg problem. Now, the city of Konigsberg, which is now modern-day Kaliningrad, was divided into 4 districts by the Pregel River, and it was connected by 7 bridges, right? So we have these 4 districts here, right? And they're connected by these 7 bridges, right? So we have Bridge 1, Bridge 2, Bridge 3, Bridge 4, 5, 6, and 7. Now, the question that was framed here was, is it possible to take a walk so that one crosses every bridge exactly one time? Okay. Now, in 1736, Euler published a paper saying that this is impossible, right? And if you stare at this long enough and you try a couple different scenarios, you'll see that you're not going to have any luck, right? Now, the argument's simple. If there was a walk, suppose the walk does not start in one of the 4 regions, for example, the island, right? So you could suppose that the walk does not start in the second region right here, right? So what's going to happen is that at some point in time, we would enter the island by crossing a bridge and then leave through another bridge, right? So let's just suppose maybe that I started in region 4, and let's say maybe I went across bridge 7, and then across bridge 4, and then so I'd enter through bridge 4, and then maybe leave through bridge 2. Okay, so I've entered and I left on 2 separate bridges here. Then you would enter on a 3rd bridge and exit on a 4th, right? So then what would happen is that you'd have to enter here and then exit here. And then we would have to come in through here, but now we're stuck, right? And I didn't get to bridge 3 yet, right? So now what this means is that the walk must start or end on the island, right? However, if you try this for any of the other districts, you're going to end up with the same conclusion. Now, of course, the other idea is that you could, of course, form an exhaustive list of all the possible routes, but this would be impractical, right? Because you're going to get a large number of lists, a large number of possibilities here. And if you wanted to generalize this to like a larger problem, it would be even more impractical, right? So what Euler did is he formulated a general criterion for any number of islands or bridges. And this is usually considered as the first theorem in graph theory. However, graph theory was not formulated as a subject for over a century later. So this is sort of interesting here that we get a theorem about graph theory without it even being invented yet. Now, what we're going to do before we sort of summarize his findings here is we're going to restate everything in a graph theory setting, right? So we're going to consider each district as a node, right? So districts are nodes. Now we need to allow for parallel edges, which are edges, of course, connecting the same nodes, for the reason of things like bridge 5 and bridge 6, right? Because both of them connect region 2 and region 4. So we need to allow for parallel edges. Now, we define a walk to be a sequence of nodes with any 2 consecutive nodes connected by an edge, but with the possibility of multiple edges between the same 2 nodes, right? So that's our sort of our parallel edges thing. Now, a walk in a graph with parallel edges is, of course, a sequence V0, E1, V1, E2, V2, so on and so forth, where we have the V's representing the nodes and the E1 through EK are edges with the EIs connecting VI minus 1 and VI, right? So essentially what we need to see here is that each pair of nodes is connected by some edge. Now we're going to define an Eulerian walk to be a walk that goes through every edge exactly once, right? So for example, we have an Eulerian walk here because if we were to follow along this path, then let's see, it looks like here we're then going down here. I already messed it up, but it looks like, you know, if this was done right, then you would pass through every edge exactly once. It looks like I think I need to maybe start. Let's try this again. So if I start, I think if we start, oh, okay, I see what I did. I think I followed it wrong. So we go here, and then down here, there we go. So we were able to go through every edge exactly one time. So now we can finally say what Euler said, of course, in modern graph theory language, that if a connected graph has more than two nodes with odd degree, then there is no Eulerian walk. If a connected graph has exactly two nodes with odd degree, then it has an Eulerian walk. And every Eulerian walk in this form must start at one of these and end at the other one, right? So it's going to start at one of the nodes with odd degree and then finish at the other one with the odd degree. And if a connected graph has no nodes with odd degree, then it has an Eulerian walk, but all of these are closed, right? And that was, of course, the example that we looked at here. It looks like all of our nodes have either degree 2 or 4. Okay, and the proof is in the textbook. We're not going to go over it too much because I'm not going to really harp on the details for this, but if you're interested, that's where you can find it. Now, a nice concise way to restate this is that a connected graph has a closed Eulerian walk if and only if every node has even degree, right? And of course, we also need to allow for the fact that we can have exactly two nodes with odd degree, right? So we need to be aware of that as well. Now, which of the following graphs have an Eulerian walk? Well, of course, if we look at part A, it looks like this degree right here has degree 3. And it looks like so does this one, but so does this one and this one. So since there are more than 2, in this case 4, nodes with, I think this should be odd degree, right? Yeah, this should be odd degree. Right, so there's more than 2 nodes with odd degree, so that one does not have an Eulerian walk. Now, it looks like we've now fixed in part B those problem nodes, and they now have degree 4. Now, of course, this makes all nodes have even degree. So that's not only going to have an Eulerian walk, it's going to have a closed Eulerian walk, right? So closed Eulerian walk since all nodes have even degree. Now in part C, it looks like we have this node has odd degree. And let's see, it looks like, let's see, sorry, no, that one has even degree. And then this one has even, this one has even, this one has even, but these two are odd. So since it has exactly 2 nodes with odd degree, that will have an open Eulerian walk. And of course, it has 2 nodes with odd degree, right? And of course, the idea behind this one is that we'd have to start here and end at the other one. So we might do something, let's see, let's try something like this. Ooh, it looks like I already messed it up, right? Oh, I guess not. No, that would work. Yep. And then in part D, of course, if we look at all of these, it looks like they all have even degree, I think. Yes, yep, so they all have even degree. So of course, that will be another one with a closed Eulerian walk. Okay, now the last thing that we'll address in this video is the idea of a Hamiltonian cycle. And this is a cycle that contains all nodes of a graph. Now this is similar to an Eulerian walk, but instead of every edge being crossed exactly once, we're hitting every node exactly once. Now, unfortunately, much less is known about these, right? So we don't have the nice results that Euler came up with. Okay, now we have two famous graphs here. We have the dodecahedron graph and the Peterson graph, and we want to know which one of these is a Hamiltonian cycle, right? So it looks like if we maybe start here, we could maybe do something like this. Come around here, and I've hit all the nodes on the outside, and I don't care about the edges, so I don't need to cross over again. So we can then come in here and maybe do something. Let's see, what's the best way? I guess we want to do something like this. And then again, I don't care about going to this node here, so we're just going to go right to here, and then we can come around this way. And that's the Hamiltonian cycle. Right, now for the other one, you're not going to have as much luck, because now if you try and do sort of the same strategies before, you can now get in here. But let's see, it looks like one option is to go here, and then we can go this way, and then this way, and this way, but that's not right because it looks like we can do that one. I thought maybe when I was doing this we could not, but let me double check this again. So let's erase this. So if we start here, come around here, maybe this is one. Let me just double check this one. Okay, and now see my problem. So the one thing that I'm forgetting here is that these need to be cycles, right? So they can't just be a path that connects all of these. We need specifically a cycle, right, that is going to contain all of these nodes. So let's try this again. So in the first one, I might be able to do, let's see, let's try something. Let's do something maybe like this. So we come around here. Maybe let's do this. Okay, so that's not what we want to do. But the idea is that this one does, and this one does not. All right, let's try this one again. And then if not, maybe I'll just leave it as an exercise since I can't do it right now. But let's see, let's maybe try something like this. No, that's not going to work either. I need to somehow... Okay, let's try this maybe one more time. So I want to start maybe... Let's try doing this the way I did before. And then go in here and we'll get all this. Wait a minute. Here we go. I think I can do it now. So instead, I'll go this way. Maybe not. Okay, so maybe I'll leave that one as an exercise since I can't figure that out on the spot right now. But this one, if you can find it, this one does have a Hamiltonian cycle, whereas this one does not. Okay, so that concludes this video on Eulerian walks and Hamiltonian cycles. I hope you enjoyed, and I will see you next time.